Yeah, it's great being here, and happy Valentine's, everyone. I'll be talking today about some recent developments on our understanding of different transients and galactic nuclei, that is, flares that we see from around supermassive black holes in distant galaxies. So a lot of this work has been done with a list of many of my excellent collaborators, and they're listed here also names of a few of the students who I've interacted with on some of these projects. So I'm a theorist working on time domain phenomena, which means that I spend a lot of my time thinking about transients. So loosely defined, transients are astronomical events that appear and disappear in the night sky over human timescales. Some would argue that maybe the right comparison is to a PhD timescale. There are different types of transients that I'm interested in. So broadly speaking, one category is that involving stellar explosions, such as supernovae, or gamma ray bursts, kilonovae, and so on. These involve the violent deaths of stars as they deplete their nuclear fuel, maybe undergo core collapse, maybe interact with neighboring stars, producing gravitational waves and different types of fireworks. And another class of transients that I study are those associated with galactic nuclei. So they often involve the premature destruction of stars that have happened to somehow interact with the supermassive black hole or its extreme environment, destroying the star and producing a bright flare. And this will be the main topic of this talk. All right. So as I said, galactic nuclei transients. Okay. They often involve.
Me too.
Okay. Got rid of that feedback, or maybe not.
All right, I'm going to leave the meeting on that.
Okay.
Let's monitor.
So they are generally these sort of transients are, as I said, driven by some interaction of stellar objects with the supermassive black hole in the center of a galaxy. So just to set the stage, we're thinking about processes happening in center of galaxies where we have one supermassive black hole and millions of stars and stellar objects, possibly gas. And we're thinking about processes that happen within what we call the radius of influence. So this is the distance within which the gravitational potential is dominated by the central supermassive black hole, which means that stars follow roughly Keplerian orbits within that volume. And for a typical galaxy, for a typical supermassive black hole mass, this is roughly of a parsec scale. So this is the volume containing about twice the mass of the supermassive black hole, which could be millions or billions times the mass of a sun. And within that volume, we have millions to billions of stars. So it's this high density of stars within this relatively small volume and the presence of the supermassive black hole that gives rise to different interesting dynamical processes that we think about. And this cartoon kind of summarizes a lot of these different processes that we think about in this context. So I'll just go over a couple of these examples. So for instance, we might have stellar mass black holes that inspiral towards the supermassive black hole by the emission of gravitational waves. These produce millihertz gravitational waves, which future space-based missions like LISA would observe. We call these extreme mass ratio inspirals, or EMRIs. We could also have TDEs, or tidal disruption events, which occur when stars approach the supermassive black hole on nearly parabolic orbit. If they happen to pass close to the black hole, they get shredded by tidal forces that produces a flare that we now commonly see. Alternatively, stars can also approach the supermassive black hole by the emission of gravitational waves, inspiraling towards it on a more circular orbit, maybe starting to overfill the Roche lobe, shedding mass to the black hole. We call these circular TDEs. Quasi-periodic eruptions, or QPEs, will be a main focus of this talk. I think they're related to the interaction of stars with accretion disks around supermassive black holes. If we have binaries within this radius of influence, they would occasionally pass near the supermassive black hole, and they could be split apart in a 3-body exchange interaction. One star might get ejected as a hypervelocity star, and at least in the Milky Way, we think we've seen several of those. And the second star will remain bound to the supermassive black hole, maybe producing the so-called S stars. And we could also have direct collisions between stars due to the high density and high velocity dispersions within this region. So all of these different processes are kind of my topics of interest. And today I'll focus on some of them. Generally, we are interested in various questions related to these processes. So for instance, what are the dynamical effects that govern their formation? What are their multi-messenger signatures? How can we observe them and what would they look like? And more generally, how can we use these observations to study supermassive black holes, galactic nuclei, accretion onto the black hole, and so on. So this is connected to, I would say, a broader range of questions that we may have regarding supermassive black holes and black holes in general. So for instance, how do black holes form in the early universe? Question about the presence of intermediate mass black holes, the origin of the connection between supermassive black holes and their host galaxies, the accretion onto the black hole, the formation of jets. So all of these questions are kind of the main motivation why we use nuclear transients to study these environments. And this is kind of broadly part of an array of different approaches to study supermassive black holes. I've listed here a few different approaches that are being used. So for example, we can focus on the supermassive black hole that is in our own backyard, Sagittarius A star, monitor the motion of stars around it, study its mass. With EHT, we can also explore the horizons of a couple of supermassive black holes. A lot of the work and our understanding of these objects has been through active galactic nuclei. So these cases where the supermassive black holes happen to accrete large amounts of gas from their environment and shine brightly to cosmological distances. We could also use pulsar timing arrays to study the population of supermassive black hole binaries in the universe. And the last two approaches that I've listed here involve studying gravitational waves emitted by small objects in spiral into the supermassive black hole. So these are these MRIs that I mentioned, and nuclear transients, which I also touched upon. So I will focus on these kind of two branches of ways to study supermassive black holes. And why would processes of stellar destruction be useful for understanding supermassive black holes? So for one, these are relatively rare events. So in a galaxy, these processes happen roughly once every 10 to the 4, 10 to the 5 years. So this is less than 1% the typical rate of supernovae. Or they're quite energetic. So depending on the different types of transients that we study, but in principle, significant fraction of the rest mass energy of a star destroyed in this environment could be converted into radiation that we could observe, which means that we can observe them to cosmological distances. The emission is at least sometimes dominated by scales of a few gravitational radii, which means that we could also hope to study the properties of the supermassive black holes, like their mass and spin, by understanding these transients. Importantly, these sort of transients could illuminate a population of otherwise dark supermassive black holes. So I've mentioned these active galactic nuclei, AGN, but most of the systems, most of the supermassive black holes are otherwise quiescent. We don't see any radiation from them. So in the rare cases where a star happens to be destroyed in these galaxies, we may get a glimpse into a supermassive black hole, which otherwise we can't see. And finally, at least in some of these cases, we expect there to be a signature in multi-messengers, which means that we could use an array of different methodologies in multi-messenger astronomy to study these systems. So I'll be focusing on some recent discoveries, some new types of transients that have been discovered in the last couple of years. And specifically, I'll be talking about what we call repeating nuclear transients. So aside from stars being destroyed and being a one-off event, there are now classes of events where we see repeated flares from centers of galaxies. And specifically, I'll focus on this subclass called quasi-periodic eruptions. So just kind of to set the stage. So prior to 2019, we've seen supermassive black hole or the emission around them to show variability in different forms. So in AGN, we know that AGN display variability in different bands over different time scales with different sorts of amplitudes and so on. And this is seen in optical and in X-ray for different examples. So this typically doesn't have a distinct clear structure or any sort of clear periodicity. So that's why it came as a surprise where in 2019, these sort of flares were first detected. So what I'm showing here is the X-ray light curve observed from the center of this galaxy GSN 069, which was detected in 2019, showing soft X-ray flares that repeat every roughly 9 hours in this case. So also kind of in the context of Valentine's, we can think about this X-ray light curve as being the heartbeat of a supermassive black hole in the center of that galaxy. So I'll dive now a bit into describe what these flares actually look like, what are the observational properties, and then I'll continue to discuss the theoretical understanding of what causes these flares. So there are now 8, maybe even 10 such sources that have been detected. They show periodicities that range from a couple of hours to maybe a couple of days. The duty cycle, so the duration of the flare relative to the time between the flares, is of order 10% or so. And they show luminosities of roughly 10 to the 42, 10 to the 43 ergs per second. And the flares are, as I said, are in soft X-rays. So if you assign a temperature to the flare, it's roughly 100 or 200 electron volts. That's slightly hotter than the emission seen between the flares, which we call the quiescent emission. They seem to occur around supermassive black holes of roughly 10 to the 6 solar masses, although these estimates are quite rough, given from galaxy scaling relations. Okay, so taking a closer look at the flares themselves, we see that they show this interesting behavior seen in different bands. So for example, here the flare is, so the flare seen in different bands is normalized to the peak. So you can see how it rises more rapidly in the harder bands, and then the slower bands, it has this more gradual rise. And also the decay is faster in the harder bands versus the softer bands. Here, if you phase fold several of these flares on top of one another, you see the rise from some quiescent emission all the way to peak and back. And then you can plot the evolution of the spectrum. So this is the spectrum as a function of energy. You can see how it rises. So the flares are characterized by the quiescence going to a hotter and brighter state and then going back. But they also have this interesting behavior where if you plot the luminosity versus temperature, it seems to show this sort of hysteresis loop. So the flares are not symmetric on the rise and on the fall. This is clearly seen here as well. So this is simply a manifestation of what I discussed here. But they always show this counterclockwise behavior where the rise is hotter than the decay. And it seems like the spectrum of the flares themselves and also the quiescence is relatively well described by some green tail of a black body emission, although I'll get back to that and discuss some of the details. So one interesting clue about these flares is that at least in some of the systems, they appear to show this interesting regularity, where the timing of the flares is alternating back and forth between slightly shorter and slightly longer flares. So for example, it might alternate between 8 hours to 9 hours, 8 hours, 9 hours, and so on. So this is seen here, showing the time between consecutive flares. You can see it alternates back and forth. This is for another system. And usually these deviations are indeed of order 10% or so. If you stack the light curve, accounting for the sum of two consecutive flares, then you can see how they stack up nicely. While in other systems, the timing of the flares seems to be more erratic with no clear long, short alternating behavior. So that is one interesting clue, which was important in the model that we proposed. Another interesting point is that QPEs are generally rare. So we don't really know what their lifetime is. We've only seen them since 2019, and it's not clear whether they last several years or decades, but we can say something about their prevalence. So what fraction of galaxies show QPEs in a given time? And from the few QPEs that we've detected with eROSITA, which is sort of a blind survey, we can say something about it. And it seems like QPEs happen roughly in about 1 galaxy per 10 to the 4, in 1 galaxy per 10 to the 4 galaxies. If you want to translate that into rate, you need to assume something about the lifetime. Seems like the formation rate of these sources should be roughly 1 per 10 to the 5 or 10 to the 6 years. Okay, so now I'll move on to the interpretation of these sources. And I would say that any successful model should, at least the 0th order level, be able to explain this list of observables. So for example, things that have to do with the timing of the flares, so their periodicity, the duration, this behavior that some systems have this long, short alternation, different properties about the emission that I've mentioned, also these associated properties like the hosts of QPEs, the preference maybe to low supermassive black holes, their abundance. I would say that some of the key features are those highlighted here. So the fact that they show this long, short alternation, this interesting evolution of the flare spectrum, and also these associated properties, which I'll get back to later. So we're currently in this state where the number of proposed models is definitely exceeding the number of sources. So there've been a lot of different ideas proposed in the last few years since they were discovered. I don't have time to go into the detail of all of these, but broadly speaking, some of the models have proposed different sorts of disk instabilities. So we know that radiation-dominated disks, at least theoretically, should have this interesting behavior of instabilities. So the idea here is that if the disk undergoes an instability, then the inner regions of the disk could alternate in terms of the accretion rate, and that will lead to changes and possibly the appearance of these flares. And another important class of models are those involving a supermassive black hole and some orbiter, where the orbiter is in a way a clock that sets the recurrence of these flares. And here there are also a number of different submodels. And I'll focus on this class of models, the orbiter and disk interaction, which currently seems to be like the favorable solution or explanation for what these QPEs actually are. So we proposed a model a couple of years ago that tries to explain these QPEs. And the basic idea is explained here in this cartoon. So we have a supermassive black hole, and it is surrounded by some accretion disk. And there is also a star, a main sequence star, on an inclined orbit with respect to the disk. And this star collides with the disk twice per orbit. And the flares in our model originate from the collisions of the star with the disk, where some shock-heated disk material gets ejected and cools and produces the flares. And the quiescent emission, that is the emission seen between the flares, is originating from the inner part of the disk. So a few aspects of this model is that, for instance, the timing of the flare will be subject to the precession of the orbit, possibly the precession of the disk. And I'll also talk later about the origin of the disk and some of the ideas around that. So one thing that we get for free from this sort of picture is this behavior of long and short alternation of the flare recurrence time. So the time between two consecutive flares will be slightly longer when the star passes through apocenter and slightly shorter when you pass through pericenter. And for a general configuration of the orbit relative to the disk, the relative difference will be of order of the eccentricity of the orbit. So to explain deviations of roughly 10%, we need to invoke an eccentricity of roughly 0.1. Later on, when I'll discuss the dynamical formation, it actually appears like this eccentricity is the typical eccentricity we expect these systems to form with. Talking about the formation of the flares themselves. So when we have a star plowing through a disk, it will sweep up some of the disk material. There won't be any significant gravitational focusing because the collision is so supersonic and much faster than the escape velocity from the star itself. So it basically just sweeps up more or less the geometrical cross-section of the star. There's some caveat to that we think that these stars actually get ablated and become slightly more puffy than just a regular unperturbed main sequence star. But if you assume a standard disk, where the requirement here is that the disk should be radiatively efficient such that we'll have the quiescent emission that we're seeing, that gives you an estimate of the amount of mass being swept and the amount of energy initially injected into this shock-heated material. And the velocities involved here, so that's the shock velocity, which is comparable to the Keplerian velocity, is roughly 0.1 c, which is what you get for stars that repeat every few hours around the supermassive black hole. We've been simulating this process as well. This is a paper that is about to come out, led by Xiaoshen Huang in Caltech, using radiative hydro calculations, basically slamming a disk against a star and following the evolution of the ejecta associated with this interaction. You can actually see that, interestingly, you get an injection of mass both in the forward direction. So in this case, the star is effectively moving downwards with respect to the disk. So some of the material is ejected in the forward direction, but you also get this plume in the outward direction, which is comparable in size and also in mass content to the forward one. And one intuitive way to understand this is if you think about this example, the terrestrial example of an apple being pierced by a bullet. So you must have seen this image before, and you see how you get this more or less symmetric ejection of apple ejecta, both in the forward and backward direction. You can try and guess which way the bullet actually went. So by a show of hands, you can point either right or left. That's the time to do it. Okay, more or less 50. Well, I think most of you got it right. Yeah, that's where the bullet is going to. Okay, so what would the flare actually look like? So initially, this shock-heated material is very optically thick, so most of the photons are trapped within it. So it has to expand quite a bit before the radiation can leak out. So the condition for the radiation to leak out is that the photon diffusion time will be similar to the dynamical expansion time of this cloud. That gives you this common criterion where the optical depth needs to go down to roughly C over V, roughly 10. If you account for the rate at which the optical depth goes down and for the adiabatic degradation of the internal energy of this shock-heated material, then you get an estimate of the luminosity and also the time scale over which most of this emission comes out. They both seem to be in the right ballpark. The temperature of the flare is a bit more subtle. It turns out that the emission is not purely black body. There's simply not enough time to produce all the photons when the star passes through the disk and when this material is highly compressed. Turns out that you're not producing enough photons to sustain thermal equilibrium, which means that the effective temperature is boosted to slightly higher, hotter temperatures, giving you this typical range of roughly 100 electron volts. And recently with Indrik Wurm and Brian, we've looked into this, studying exactly these processes of photon production and the shock right ahead of the star as it passes through the disk, and the subsequent expansion of this cloud using gradiative transport Monte Carlo calculations. And these calculations seem to, at least qualitatively, reproduce all of the observable features like the rise in the harder bands versus the lower bands. And you can see also the reproduction of this hysteresis loop that I mentioned. So the evolution in this luminosity versus temperature diagram. So this model naturally accounts for that. And we also get the right temperatures more or less to explain the observations. Here, for example, I'm showing the disk emission. And on top of that, the emissions seen from the flare as a function of time. And you can see this more or less vein-like tail of the flare on top of the vein-like tail of the inner part of the emission, of the disk emission. And that's our model for the emission seen in these sources. Okay, so now how did these systems actually form? So to address that, one question we need to ask is what is the origin of the disk that we're invoking here? So there are a few possibilities. One is that the disk itself is formed by Roche lobe overflow from the star. So if the star happens to overfill its Roche lobe and shed some mass, maybe it forms a disk with it, which it can then later interact and collide. Another alternative is that the disk was already there, simply an extended AGN disk. And the third option, which we like, is that the disk has formed from another star undergoing a tidal disruption event in the same system. So I've mentioned tidal disruption events at the beginning of this talk, but I'll go into some detail just to get everyone on the same page. So this is the process that happens when a star falls almost radially onto a supermassive black hole. And if it penetrates a distance called the tidal radius, where the self-gravity of the star is matching the tidal forces from the supermassive black hole, the star gets stretched and destroyed, as shown here in this cartoon by Martin Rees. Then this stripped or this shredded stellar debris attains an energy spread. So some material gets accelerated into positive energies, causing that part of the star to be unbound and escape the system. And half of the star remains bound to the supermassive black hole and falls back. The fallback rate of the most bound debris is of order a month, and that will typically set the time scale over which the flare seen from these events will evolve. It will then, the fallback rate of the bound material will fall as a parallel with time with this famous t to the minus 5/3. And the idea is that, at least in late times, this infall of bound stellar debris will circularize and form a disk with a radius of roughly a couple of tidal radii. And eventually, this material will accrete onto the black hole. So we've been observing TDEs for the last couple of decades. And by now, there are about 100 TDE candidates. They show a variety of different behaviors, especially in the optical. There's this whole zoo of different TDE characteristics that have been seen. There's still some open questions regarding what forms the early time optical emission in TDEs. Is it related to some collision of the streams of the stripped stellar material? Is it related to reprocessed accretion? We are also seeing radio flares at late times, which may have to do with outflows originating from these systems. But it seems like in late time, there's a pretty solid understanding where if you look at the late time X-ray optical and UV emission, they show what you would typically expect from a time evolving thin accretion disk that is feeding the black hole, simply the remnants of the star that are slowly feeding the black hole. So it has this typical gradual decay in X-rays and this typical UV and optical plateau, which is what different models actually predict. So in late times, we think that we're actually seeing a bare disk, at least in some of these TDEs. So back to QPs, actually prior to just a few months ago, there was some evidence tying QPEs and TDEs together. So at least in a couple of systems, before the appearance of QPEs, you've seen this gradual decay in X-rays that is more or less consistent with what you would expect if a TDE actually happened in that system, although there was no definitive detection of a TDE prior to the appearance of QPEs. So this is true for a couple of systems. The hosts of QPEs also seem to be more or less consistent with what we know the hosts of TDEs are. So there was some tentative evidence which led us to suggest that maybe QPEs are formed when we have an MRE and a TDE. So MRE plus TDE equals QPE. And the idea is that if you have a star orbiting the supermassive black hole on an orbit of several hours to a day, it will stay there for quite a while. So the gravitational wave in spiral timescale for such a star is roughly 1 million years. Now, tidal disruption events happen in a given galaxy roughly once every 10 to the 4, 10 to the 5 years. So almost inevitably, if we did have an MRE around the supermassive black hole on the right separation, it will interact with a TDE sometime during its slow in spiral. And then you would get an accretion disk. The MRE was already there. It will now start colliding with the disk, and that will produce these QPEs. So this explains several aspects. For example, this association between QPEs and TDEs. The delay time may be related either to the time it takes the disk to actually form and settle into a thin disk, or maybe if it's set by the viscous spreading of the disk, we may have to wait for the disk to intercept the orbit of the MRE. The periodicities that we're seeing also naturally explain why QPEs appear to have periodicities of order hours. So if you think about the orbital period at the tidal radius, which is roughly the size of the disk that is formed, it's by definition similar to the dynamical time of a main sequence star, which is of order hours. So that kind of naturally explains why we're seeing QPEs with those periodicities. And we also predicted, based on some arguments regarding the dynamics, that a significant fraction, maybe 1 or 10% of TDEs should actually host QPEs. And indeed, a few months ago, there was an interesting case, this TDE called 2019 QIZ. It was detected in 2019 as a completely standard vanilla TDE, had this typical optical flare consistent with many other TDEs. And in late times, it showed this gradual decay in X-rays and this optical and UV plateau. Nothing special about this TDE. And then there were some follow-up observations trying to study and characterize the disk that has formed in that system. So we're talking several years after the TDE has occurred. And then some Chandra observations. So this is the source, this is the galaxy. Suddenly showed this interesting rebrightening of the source that appeared and then disappeared. So that's called for longer duration observations in X-rays using NICER, which then showed this nice repeating sequence of flares, basically QPEs in that system, with a period of roughly 2 days, which means that the orbital period of the orbiter that is producing these flares is 2 or 3 days or 4 days, depending on whether we see one flare, one collision per orbit or both collisions. You can also study the extent of the TDE disk by looking at these late time observations. And it actually seems like in this case, this is the disk profile. So the surface density versus radius. It actually seems like the outer edge of the disk is entirely consistent with the position of an orbiter with a period of 2 or 4 days. And this is an independent measurement, right? So here we're just using the late time observations of the disk, inferring its size, and it seems to be consistent. And this is has some interesting consequences. For example, the possibility of detecting more QPEs by doing the same exercise, following up with X-rays, TDEs that have happened a few years ago. So I'm showing here another study of one of the QPE sources, also characterizing the disk associated with it. It also seems that the disk you infer for this source actually has an extent that is outside the size of the orbit required to produce the periodicity that we're seeing in this source. Okay, so I've mentioned these two very distinct channels where stars somehow interact with a supermassive black hole. One is a TDE, where a star comes from far away and plunges into the black hole on this nearly parabolic orbit. And the other scenario where a star approaches the supermassive black hole is an EMRI. So how do these different processes actually occur in galactic nuclei? So to answer these sort of questions, the typical machinery we use is this Fokker-Planck formalism describing how different orbits or populations of orbits evolve in galactic nuclei and reach the supermassive black hole or reach sufficiently low angular momentum orbits. And this encapsulates these different processes like two-body relaxation, causing stars to exchange angular momentum and energy when they pass nearby another. And that leads to this effective diffusion in phase space. But a more intuitive way to look at all of these processes is through this schematic phase space that I'm showing here. So here on the vertical axis is the pericenter distance of different orbits around the supermassive black hole. So this is related to the angular momentum. And here the horizontal axis is the semi-major axis of an orbit related to its orbital energy. So the diagonal here, that's where circular orbits sit. Nothing is here because the pericenter is always smaller than the semi-major axis. So most stars within this outer radius that I defined of the radius of influence, a couple of parsecs, sit around here on orbits that are comparable to the radius of influence with eccentricities that are mild, say roughly 0.5. So if you start out with a population of stars around there, they will start to evolve due to these two-body scatterings and other relaxational processes, which will cause the orbits to diffuse in this phase space. So orbits will start to become more eccentric. It turns out that the diffusion time in angular momentum is shorter than the diffusion time in energy for these eccentric orbits, which means that orbits will evolve primarily up and down along this line, just changing in angular momentum, but preserving the same semi-major axis, until they occasionally reach this critical pericenter distance of the tidal radius, and that's when you get a TDE. If you start with orbits with smaller semi-major axis, they will also evolve this diffusive evolution in phase space. But once they reach this green line, that's where gravitational wave evolution becomes faster than the evolution due to these relaxational processes, which means that they will be captured and will begin to circularize quite rapidly by the emission of gravitational waves until they approach the supermassive black hole on nearly circular orbits. That's how EMRIs form in this simplified picture. Another important process that can take place is Hill's mechanism, which I mentioned in the beginning, where binaries get split apart by tidal forces. So one star gets ejected as a hypervelocity star, the other star remains bound. So these stars that remain bound occupy this red dashed line. We actually think that their rate is dominating the feeding of EMRIs. So basically the formation of EMRIs may be dominated by the rate at which binaries within the radius of influence get split apart and inject stars into these deep orbits that can then be circularized by gravitational waves. And just to kind of give a local example and think about these processes, so if you think about the New York City subway system, it's very easy to go uptown and downtown, but it's actually quite hard to go east-west. So this is exactly what stars experience when they travel within this phase space. So we can calculate the rates of these different processes. I won't go into the details, but for example, the TDE rate is essentially set by the orbital period at around the radius of influence, which is related to the velocity dispersion of the galactic center. You get this typical 1 TDE per 10 to the 4 years. The rate of EMRIs, as I've mentioned, is probably dominated by the splitting of binaries. So the main quantity that sets this rate is the fraction of binaries within the radius of influence. We don't really know what this value is, but if we want to be conservative, maybe it's 10%, which means that the rate of formation of EMRIs will be roughly 10% of the rate of TDEs. And that also means that the average number of stars located around these interesting orbits that could produce QPEs in a given time is given by this rate multiplied by the time they spend there, which I mentioned is about 1 million years, which means that in every galaxy, there's of order unity such star in a given time, waiting for a TDE to happen, possibly producing these QPEs. Different questions that could be asked. So for example, what's the fraction of TDEs followed by QPEs, which I mentioned, and can these stellar MREs survive multiple events of TDEs? That will determine the rates at which we detect these QPEs. So I'll just mention some recent work by Philip Yao in Princeton that has looked into the rate at which stars get ablated as they repeatedly cross these disks at point 1C. Turns out that there's kind of a significant rate of ablation, which might be the limiting step for these QPEs to survive. Another possibility is that if these stars eventually do approach the point where they overfill the Roche lobe, you can get an interesting type of transient that we recently studied. So in this case, the star will begin to shed mass, and this process will be unstable, so it will accelerate in a way, and that will eventually lead to very super Eddington feeding rates from the star onto the supermassive black hole, and may produce this bright optical flare, not too different from what we see in a regular TDE, which will eventually evolve into an X-ray emitting disk. So this is these circular TDEs that we recently studied, made some predictions about some interesting observable features. So unlike regular TDEs, they will also have a precursor associated with the disk that has formed before you have this super Eddington outflow. I'll finish by saying a few words about some ideas related to the formation rate of LISA sources, so millihertz gravitational waves. So just to remind you, LISA will be sensitive to gravitational waves in this millihertz frequency range, so between LIGO, between pulsar timing arrays. And one of the key objects that LISA will see are exactly these black hole MREs. So stellar mass black holes that are inspiraling towards the supermassive black hole emitting gravitational waves. So with Barak Rom at the Hebrew University, we recently worked to calculate the rate, or what LISA will actually see, using sort of the same formalism for the dynamics within galactic nuclei. The bottom line is that we expect LISA to detect many sources, maybe thousands of high SNR MREs over the course of a few years. There will actually be so many stellar mass black holes orbiting supermassive black holes that if you account for the large population of galaxies that will be within the LISA detection volume, they'll actually dominate the gravitational wave background at a range of frequencies, even more so than the galactic binaries, which are expected to be an important contribution to the noise in LISA. So just finishing with some words about kind of ideas and bigger questions. So how do we detect more such QPEs? So far, we've detected them mostly through large surveys like eROSITA, which is unfortunately now off. So one way we could in the future find more of them is through this idea that we can follow up with X-rays TDEs that have already happened. And to do that, we need to better understand the dynamics that are prevailing in galactic nuclei. So what will be the distribution of stars around supermassive black holes that these TDE disks will intercept? So that is one idea that is currently being pursued, and there are several such proposals that will take place in the coming months. Another question is, we've only detected QPEs in X-rays so far. Are there any analogs in other bands? So we recently looked into that, and we think that in some cases, depending on the disk properties and the orbital separation of the MRE, the flares that I've discussed may actually stick above the disk emission in the UV rather than in the X-rays. That has some interesting prospects in light of ULTRASAT, which will be launched in the next couple of years. And we expect ULTRASAT to actually detect several such flares. More broadly, one could ask what is kind of the big observational landscape of such interactions between stars and disks, which should probably be common in galactic nuclei. Are there any non-thermal components? And what are the rates of these different sorts of events and interactions between stars and disks? So in the context of gravitational waves, one could ask, can these QPEs actually serve as multi-messenger electromagnetic signatures to LISA sources? So people have looked into this. If you consider the known QPE systems, they all seem to be just out of sight for LISA. This has to do with the fact that QPEs are relatively rare, so we don't have a lot of sources that are nearby. Maybe in the future, we may be lucky and have one more nearby QPE source. But I think more importantly, we can actually think of these QPEs as an interesting probe to understand the dynamics that produces LISA sources. So it's exactly the same processes that end up putting stellar mass black holes near supermassive black holes, producing MREs that produce QPEs. So in principle, we could use this as a probe of the dynamics in galactic nuclei, and also to better understand the role of, say, AGN in producing MREs, the so-called wet MREs, questions about loss cone dynamics, and so on. QPEs could also serve as interesting probes of different physics. So for example, if you look at sufficiently long baseline of the flare timing, that could allow you to constrain the orbits and their precession. And these will be sensitive to both the supermassive black hole mass through the apsidal precession, but also the spin through nodal precession, which will happen on years timescales. So with sufficient observation, there is some hope that QPEs would actually be really amazing sources to study supermassive black holes and their spins. So that is one interesting idea. Since they also interact with the accretion disks, they can be thought of as mechanical probes of the accretion flow around supermassive black holes, which is quite a unique concept, which we don't have access to otherwise. So for instance, over sufficiently long timescales, we may detect some decay in the orbital period of these flares associated with the drag that the stars experience as they repeatedly pass through the disk. So through that, we could constrain, for instance, the surface density of accretion disks at different states. I didn't touch upon a broader class of repeating nuclear transients. Many of them are referred to as repeating tidal disruption events. So the idea is that in some cases, a star might just graze the tidal radius. So just some of its mass will feed onto the black hole, but the star will then eventually repeat and come back to another visit. So there are a few examples of such sources where we think that these repeating partial TDEs occur. There are some interesting questions about the connection between this class and QPEs. I don't have time to get into that, but I can address that in the questions. And just kind of to finish by prospects for this field. So over the next few years, we'll have many additional surveys studying the sky in different bands, anything from radio to X-rays and gravitational waves in the millihertz frequency, maybe on a decade time scale. And one interesting point to finish with, so with LSST, which will come online in the near future, we'll detect many more transients, and specifically many more nuclear transients. So estimates talk about maybe 10 to the 4, 10 to the 5 TDEs over the course of a few years using LSST. So roughly 10 TDEs every night. So in principle, if we follow up some of these TDEs, and even if just 1% of them actually host QPEs, it means that we'll have roughly 100 new repeating nuclear transients every year. So there will be a lot of new opportunities in the coming years for this field. And last slide, I'll just finish with kind of mentioning kind of the broad range or the bird's eye view on this field. So the hope is that we could study galactic nuclei and supermassive black holes and accretion onto the supermassive black hole using nuclear transients and gravitational wave sources. And this all feeds nicely into these theoretical ideas of dynamics in galactic nuclei and these different emission mechanisms that I've mentioned. And by understanding them, we can better inform our understanding of the dynamics, which will kind of reflect back to our better understanding of what we expect to see in gravitational waves and transients. This is all kind of like a connected net of ideas, which we will look into in the next few years. And I'll just finish it with this summary slide and take questions.
Questions in the room? Yes, no.
So the association with the TDs is, seems quite convincing. What do we learn from not seeing these kind of things in just regular AGN more normally?
Right. Yeah, so that's one immediate question. What's wrong with an AGN disk? Why can't it produce these sort of flares? So one aspect of that is that during the migration of a star from wide separation down to these scales, if there was in fact an extended long-lived AGN disk, it will repeatedly collide with it many times before it can actually reach these small separations. So in a way, it could possibly be completely ablated or entrained in the disk, and then you won't have these high inclination collisions on the scales of hours that you need to produce these flares. I think there are still some open questions regarding kind of the role of AGN in terms of the dynamics and how stars are actually being funneled into these inner separations. But I would say that an AGN is slightly disfavored on accounts of just destroying these stars before they can actually reach these necessary separations. The other point is that in general, these flares are seen in soft X-rays. And the fact that we are seeing them is just because the veen tail of the flare is slightly sticking above the veen tail of the disk. If you have some hard component that could outshine these flares, you just won't see them. Yeah.
So for some reason, TDs don't make as corona like AGN.
Right. Yeah. TD disks seem to be very soft, which is necessary to actually see these flares.
Look at the Zoom because
I don't have the Zoom.
oh, okay.
Yeah.
All right. If anyone is on Zoom and wants to just unmute yourself and speak. Okay. Don't hear you. There. Lots of questions. Oh, Jared.
I guess sort of thinking forward to Lisa, you mentioned that these are, these things are going to be like a noise floor. Is there hope of resolving individual events or disentangling that? What is the,
Right. I kind of went quite quickly through this, but yeah, there will be many sources that are resolvable. So thousands of sources, some high SNR. There's kind of this huge question of doing the data analysis in Lisa will be a huge challenge. So this is under some assumptions, but a small fraction of them will actually kind of outshine the noise from the galactic binaries and will slightly deteriorate the sensitivity of Lisa in this range. And this is all based on fairly straightforward assumptions about the population of stellar mass black holes in galactic nuclei, from which we derive these results.
Yeah, I was also wondering about these results. This is very exciting, right? 2,000 memories. So other past predictions went as low as like 1 or none. So what did those calculations mean?
So if you look at the literature, the estimates of the EMI rates, they vary by orders of magnitude. And I think a large part of that is some uncertainties regarding the segregation of these stellar mass black holes relative to the stars. There have been different ideas in the literature these stronger segregation regimes where basically they kind of rain down due to dynamical friction by Tal Alexander and others. So we recently had some developments in that, and we find these self-consistent, effectively zero particle flux solutions where you kind of get the right distribution of stellar mass black holes and how will they segregate relative to the star. So I would say the main uncertainty in these other papers was, where do most of these stellar mass black holes actually sit within the nuclear star cluster? So we think we have a fairly solid understanding of this now, which kind of reduces some of the uncertainties.
Hope you're right.
Yeah, I also hope so.
Can I ask?
Yeah.
Is it even more, so my recollection is that people talk about massive perturbation. I mean, you focused on two-body scattering between stars, but I know people have discussed other larger bodies that could cause scattering, and
Yeah.
I think these can be more important than my recollection for the Hills mechanism, where you're seeding things from larger radii. Binaries come from somewhat larger radii, where these massive perturbers can have a bigger effect on the
Right.
So do you think that's plausible, that there could be other sources of scattering that further enhance your rates, or?
Yeah, I would say so. We were trying to be fairly conservative in our assumptions. So the dynamical picture that we study, you could definitely enhance these rates by having asymmetries, by having presence of some massive perturbers and so on. So I think in a way you can kind of treat this as a baseline, right? Even in the lack of, these more dramatic events that happen possibly after galactic mergers and so on, you would still kind of, as a steady state, have this sort of vanilla rate of events. It may be dominated by, a few kind of violent events that happen across the universe, but that is in a way a lower limit.
Maybe I'll ask one other, which is, you focused on, because we think that that's what you need to explain the observations, that it's more likely stars colliding with disks.
Yeah.
Maybe you want to say something about whether we should be seeing black holes colliding with disks.
Right.
These,
Yeah. So that's a good question. And yeah, I'll just put on this slide. Yeah. So one could ask, okay, why do we need a star? Maybe we can just replace it with a stellar mass black hole. I just said that there will be plenty of them near the supermassive black hole. So for a stellar mass black hole, the effective radius will be set by something like the Bondi-Hoyle-Littleton radius, which will be much smaller typically than the physical cross-section of a star. If you want to have the same effective cross-section that will sweep up a similar amount of mass and produce the same luminosity that we were seeing for a star, you would need to have an IMBH, basically roughly 10 to the 3 solar masses for the Bondi-Hoyle radius to be comparable to size of a star. And in that case, if you invoke the abundance of QPEs that we are seeing, that will simply mean that the rate at which these supermassive black holes grow by accreting these IMBHs will be too rapid, right? So this is kind of one argument against all QPEs being originated from IMBHs. So I think a star is probably a more natural way to produce what we're seeing. Yeah.
But if you did have that with a black hole instead of a main sequence star, could it happen close enough to the central black hole that you actually see it in the LISA signal?
I think that's slightly challenging.
Yeah.
Maybe in some scenarios, if say the orbit is some low inclination orbit, still interacting with the disk, it's say a scale of like 10 RG or so, maybe you'll have some faint flares alongside the LISA millihertz gravitational waves, maybe, but I think it's still going to be somewhat challenging. But yeah, it would be great if we could, identify certain signatures that would accompany these sources. Yeah.